Weihao cool?
Good afternoon. My name is Weihao from Monmouth University, and okay, it works now. And first, I want to introduce some of the collaborators: Jiawen and Marco from BU, and Deepak from MPI-SWS, and Jonathan from Northeastern. So data analysis, it is designed to find some properties of some populations by getting some samples. And a good data analysis, it can draw some conclusions that are generalize beyond the specific data samples. And in this area, people use the concept of generation errors to measure how well such models can predict the outcomes for these unknown, unseen new data from the populations. And the generation errors, it can be formally expressed as expected values over the distributions of these populations and of distance between the model's prediction result and the true labels via loss function. And normally, we want to have a low generation errors. And adaptivity, it occurs when the choice of the method to analyze the data set, it depends on the previous interaction with the same data set. So it happens when people they try to reuse the data set across different projects during collaborations, or when people trying to, in machine learning, they use the same data set for feature selection and regression, or in the regular exploratory analysis, when the data analysis, they trying to design which queries to run after they see the result of a previous query. And this adaptivity, it will cause high generation errors. To control these generation errors in adaptive data analysis settings, people restrict the data access to a query request. And here we only focus on the linear queries. And when these queries, they are sent to mechanisms will use some random process to make sure that the result of the queries does not rely too much on the sample data. And there are some mechanisms we can choose. For example, Gaussian mechanisms that add some Gaussian noise to the query result, or data splitting mechanisms that splits the data into different pieces, and threshold mechanisms that set a threshold for different queries. And now, naturally, we want to see is, for a data analysis, what is the better mechanism we want to use? So we focus on linear queries. So these generation errors of linear queries, it is related to the maximum of absolute values of the predicted result and the original result. And according to the theorems from Deepak, these values, it is related to three factors: the number of the sample data, and the number of the query numbers, and also the number of rounds of adaptivity. And these first two factors is easy to understand. So we'll focus on the numbers of rounds of adaptivity that can affect our choice of the best mechanisms for adaptive data analysis algorithm. And it's defined to be the depth of the chain of queries. So to illustrate this concept, I first want to introduce one example. I call it to be two-round example. And suppose we have a classifier for population P, and we have samples 400 attributes and one label. To simulate this in the adaptive data analysis, we can first run 400 non-adaptive queries, computing the correlations between attribute and the label. And then we can ask another query. I call the query for one. It depends on all these previous correlations. In this way, we can have a query graph, and every node is a query, and if we have an edge between two nodes, which means one query may rely on the result of another query. If we go back to the definition, the adaptivity is designed to be the depth of the chain of queries. In these graphs, we will have many chain of queries, and in different colors. In this case, all of the chains, it has the same depth too. So the adaptivity is 2 here. That's the reason we call it 2 round. And we do some experiment about these examples, and it shows that we fix the data size and change the query numbers, and show that in most cases, data splitting is usually a better one. Even more further, if we change this program bit and to make every query to rely on its previous queries one by one, then this chain the depth of the chain become much larger. And in this case, the adaptivity become 401. Our experiment shows that in this case, Gaussian mechanism is usually a better one. Based on these observations, we designed a program analysis that trying to statically estimate this upper bound on this adaptivity so that it can help people to identify which mechanisms we want to use and to control the junction errors in adaptive data analysis. To this end, we need to answer a few questions. The first is how to define the models for adaptive data analysis. So if we go back to the adaptive data analysis settings, first task is we need to design a programming framework so that it is able to express submitting queries to some mechanisms. And our choice is we have Y languages plus labels, and these labels used for tell people where this command it is. As for these queries, we add some primitives for the queries. And if we go deeper into these queries, we have query expression and query values. Here, we have a special symbol, chi here. Chi, it represents a row of the database. So chi A, it represents an attribute at index A of this row. Now we have these programming languages. We can express these 2 round examples in our languages. And the interesting part is at line 3, we have a query request. And we focus on linear queries, so this line 3, it means such a query request that compute the empirical means of the product of the J's attribute and the K's attribute. Now we are able to express, to write some programs. We need to define what is adaptivity. So our semantic-based adaptivity, it is based on an annotated weighted dependency graph. In this graph, every node, it is labeled variables. And every edge, it represents a main dependency between these variables, which is tracked by the trace-based operation semantics. In this semantics, the trace is a list of events. And we have 2 kinds of events. The assignment event for this standard assignment and the query request, and the test event for a conditional statement like if and while. We also have the query expression evaluation that will evaluate a query expression to its query values. Now, this main dependency between these labeled variables, it catches both data dependency and control dependency. So if we think, we say one variable A may depend on variable B, either means if we change the value of B, it may also change the value of A after B in the trace, or if you change the value of B, it may cause the disappearance of the A after B in the trace. If we go back to the graph and look at the node, we add some annotations to the node. So first one is query annotations. It tells you if this node is related to a query request or not. And we also have weight. For every node, the weight means the number of the execution times of this node appeared in the trace if we're starting from some initial trace. After we have everything ready, we will define the semantic-based adaptivity, in the form of a walk on these graphs with the largest number of query requests. And this is a graph for these 2 round examples, and we find such a walk from L6 to A5 to X3, which contains 2 query nodes. and then the adaptivity is defined to be 2. Finally, we need to statically estimate this adaptivity we just defined. We propose a program analysis tool called AdaptFun that computes an upper bound on this semantic-based adaptivity. It consists of 2 parts, the graph generation and the adaptivity estimation. The reason is that since our semantic-based adaptivity, it is based on a graph. So to estimate that, we also want to construct such a graph. And we use standard program dependency graphs and then put some query annotations by scan the code and figure out where it is query related. Also, we add some weight. As for the weight, it means upper bound on the numbers of times each variables they can be reached. So we use a technique called a reachability bound analysis to give the weight. Now we have the graph. Then we want to estimate the adaptivity by search such a graph work in this graph with a maximal query length, which means we need to traverse a graph. However, there's some challenges when we do that. It is first the symbolic expressions used in the weight. For example, in the graph, it can be k. And also the while loop will introduce some cycles in these graphs. So these 2 things make it hard to directly compute such a maximal work. To solve this problem, we propose another algorithm called adaptivity. The idea of it is to reduce this task of computing the work with a maximal query length in the dependent graph to another task, trying to find the longest weighted path in a simplified dependency graph, which is a DAG. So we simplify this graph in 3 steps. So suppose we have a graph with many cycles. We'll first partition these graphs into its strongly connected components, SCCs. And then for every SCCs, we're trying to compute its local adaptivity. The last step, we were trying to shrink these graphs by replacing every SCCs with vertices, and its weight will be the local adaptivity. After simplifications, we have a direct acyclic graph, and then we can use the BFS to find the longest weighted path. And we'll return the length as the adaptivity upper bound. And in this case, these examples, the adaptivity we find, it is the purple path from 1 plus 4k plus 1. There are also some limitations about our tool. It is not path sensitive. So for example, we have a very simple examples that has a while loop, and depending on if the iteration is odd or even, we have different query requests. And I call it to be multiple round odd. And if you look at the semantic-based graph here, B, and it shows that the weight, it is 2 over k, so it can handle if it's odd or even iterations. But like the reachability bound analysis, they will give a loose bound k for every node. In this case, our tool will give a loose upper bound. We implement these tools in OCaml and Python. And our tools will return 2 results. One is the estimated adaptivity I just introduced. Another one is upper bound on the query numbers. And there are a few examples I want to emphasize here. So we tested 2 rounds. It is precise in both the adaptivity and the query numbers. Also, this is a multiple round odd I just showed. And unfortunately, we give some loose upper bound since we are not path sensitive. Also, if you look at this a red box, we have some star here. Star means it takes too long for us to get a result because the performance bottlenecks for the reachability bound analysis to calculate the weight when it sees some complicated examples that contains multiple level nested loops. So to handle this, we also have alternative implementations for these examples that will calculate the weight quickly but imprecise. Now our last step is we use a heuristic to use what we get from our tools to recommend what mechanisms you want to use. So if the square root of Q, the query numbers, is much greater than this A times square root of log Q, we recommend data splitting. In the other direction, we recommend Gaussian mechanisms. Otherwise, we recommend threshold mechanisms. We do some evaluations to test our recommendations. And the largest regressions, some machine learning, algorithms in sklearns, and some real-world adaptive data analysis algorithms. Here in bold, it is our recommendations by our heuristics. And in red is the best performance and shows that in most cases, we give our recommendation gives the best suggestion. And I will conclude our works, and we present a static analysis tools, and it can analyze the adaptivity and for adaptive data analysis programs. A few things we want to do in the future is we want to improve this path-sensitive performance. Also, we want to design a better heuristics so that it can support more mechanisms. And finally, we also integrate these things into other adaptive data analysis frameworks like GNC. Thanks for coming, and you can find the artifact and the code. Yeah, I'm here for questions.
Thank you. Any questions, anyone? So I have a question about your evaluation. So the unit in this one here, so that's seconds, or what are we counting? The numbers. What are the numbers representing?
The numbers?
Yeah, all the numbers. Are they seconds, or what is
oh,
the
yeah,
unit?
yeah.
Okay.
It is seconds.
So what is the use case you have in mind where it makes a...
Oh, wait, sorry. It's not a second. It's generation errors. So it is, you mean all the numbers here?
Yeah, what are the numbers representing?
Numbers representing the actual generation errors, RMSE.
Okay, all right, okay, thank you.
Thank you for the talk. I had a question about the other evaluation where you listed the size of each of the benchmarks that you did here, lines of code. So the sense I get is that they're fairly small benchmarks, but I don't know the area very well. Would you say these are realistically sized benchmarks? Are these sort of small ones that you use for a first pass, or what's your sense?
It's a small ones we use we manually have these benchmarks to cover multiple loop, if, and we try to have some complicated examples. So, and finally you see some very complicated examples, and we reach some performance issues. So then we have another alternative implementation to handle these cases. But it's quite small. Thank you.
All right, thank you again.